Hello, my name is Saiid Chehade, and today I will be presenting our recent work, SINBAD, which is a novel automated breakage detection pipeline. Breakage is the main challenge faced by privacy-enhancing technologies like ad blockers that alter how the page looks and interacts with the user. Let's define breakage with an example here. Let's say we have an ad blocker that has some rules to block the banner below and block some tracker code. While it does so successfully, it also removes incorrectly many main page content and leaves this overlay, which prevents users from interacting properly with the page. The user then reports this behavior as breakage. So in essence, breakage is the inability of the user to make use of this expected functionality from the web page, either partially or completely. Let's say the ad blocker now implements new rules that fix this problem and returns the content to the site. However, when the user tries to scroll and interact with the page, they cannot. So they report this as breakage, since they cannot interact properly with the page. We refer to this breakage that requires at least one interaction as dynamic breakage. As you can see later, dynamic breakage is hard to reproduce because it requires simulating the user interactions that led to this breakage. Naturally, ad blockers want to minimize the amount of breakage that occurs from using their tools, and they do so currently using the following cycle. First, users using the latest version of the ad blocker are visiting many websites. Whenever they find that some website is broken, they report it to maintainers into forums like GitHub forums, for example. Ad maintainers of the ad blockers look at these issues and try to reproduce the breakage from instructions by the users, and they push fixes to the filter lists. And this cycle continues endlessly as long as we have new updates to the filter list. Now, we find in our study that it can take up to a month for some issues to be fully resolved, which makes the process slow, decreases user experience, and might cause a reduced adoption of users for these ad blockers. We also find that many issues take some back and forth between users and maintainers to be fully resolved, which causes many intermediary commits that don't fully resolve the breakage. And this occurs in non-negligible amount of issues. This fact will require additional care during data curation. So, in our study, we focus on trying to detect breakage from filter lists in ways that are more proactive, reliable, and at scale. Prior work in this domain can be classified into three main categories. First, we have manual checks, where we have some experts trying to perform accurate interactions that can reproduce all sorts of breakage. However, as shown previously, this cannot scale to many different sites at once. The second category of techniques uses heuristics, which are simple comparisons between visits under two versions of an ad blocker. For example, a decrease in the number of images might be indicative of breakage. While they are simple enough and require minimal overhead, our study shows that they have high error rates. On top, they don't perform interactions, missing dynamic breakage. Lastly, one machine learning technique, which is called page graph by Smith et al., that tries to cast web visits into graph representation and extract features from comparing these pairs of visits to detect whether ad blocker rules that are changed are breaking or not. While the machine learning technique scales and is more accurate than heuristic, page graph still performs no interactions and is limited to static breakage. This approach also uses a heuristic to label the dataset, which we find to have high false positive rates. On top, they include many old breakage issues that we could not reproduce. Remember when we said that some breakage issues take multiple commits to resolve? Well, this approach takes each fixing commit as a separate breakage issue, including those intermediary commits that don't necessarily fix the breakage. We also could not run page graph as is because of many deprecated libraries, so we attempted our best to re-implement its features. From the prior approaches, we find three main challenges to automatically detecting breakage. First, submitting breakage issues is subjective, as users might not, for example, care about some broken commit section on the site, but would not tolerate a broken news article they're reading. Second, we find that 25% of breakages that are reported are dynamic, which are not covered by the prior work. And finally, reproducing breakage is challenging for many factors that are out of our control, including frequent changes in the web pages themselves over time. In our study, we find that we can only use the latest 4 months of breakage issues, limiting the dataset size as possible. To try to address the previous concerns, we introduced SINBAD, which is an automated machine learning pipeline. SINBAD increases the granularity by classifying sections of the web page separately as broken or not, rather than judging the full page directly. This is motivated by the fact that a broken ad blocker version could still block a legitimate ad on some section and break another section. We approximate subjectivity by introducing the concept of saliency, which attempts to model the interest areas of the user in the web page and where they are likely to interact. Next, we try to interact with these salient areas by performing a set of interactions. And lastly, we try to manually label the full data set to make sure that we have a sound ground truth. SINBAD is a 3-part process. It starts by crawling the web page multiple times, and then we extract representations from these comparisons, which we then turn into features that we use to feed a classifier that detects whether a certain section is broken or not. And finally, we use a page level heuristic to give a label for the full page. For crawling, we crawl the page 3 times, once with the fixed filter list, once with the broken filter list, and once with no filter list for reference. For each crawl, we start by semantically segmenting the page, which divides it effectively into blocks that are meaningful, like login forms, for example. Next, we classify each block into either a salient block or a non-salient block using an in-house classifier that we train on our own annotated set of 543 sites, each annotated by at least 2 volunteers, and taking only the positive intersection of their annotations to account for the moderate agreement between annotators and the subjective nature of saliency. Let's delve a bit deeper into the choices we made for semantic segmentation and saliency classification. We need the segmentation to return meaningful groups, to be efficient, to be able to scale SINBAD, and to fit into our small curated dataset. Overall, techniques can be categorized into 3. Some segmentation works directly on the web page HTML code and its tree representation, called DOM. Other approaches use the vision models to segment web page screenshots. And finally, there are some approaches that try to use a bit of both. For our purposes, we go with VIPS, an algorithm by Microsoft that is efficient enough and still perform comparable to other more demanding machine learning techniques. VIPS is a top-down page division algorithm where it has some hyperparameters that control the granularity of the segmented parts, and it relies on both HTML features and style and position features of elements. After segmenting the page, we extract features from each block that is segmented, and we train the saliency classifier given the annotator labels that achieves an 83% area under the curve score under some cross-validation approach. After classifying the saliency of the blocks, we interact with the salient candidates, and then we log the corresponding output, including the requests that occur, the script activity, and we also encode the web page itself into its DOM representation that encapsulates the structure between elements, and we then augment it with the interactions that happen, the requests, and the errors, for example. We then compare the trees from pairs of visits we perform to extract what we call edit subtrees. These are the groups of nodes that change from one tree to the other. They could be edited, removed, or added. For training purposes, we also label each subtree as either a legitimate change, a breaking change, or a neutral change. And this happens by looking at where the changes come from and what is the type of change. For example, if some subtree is removed going to a fixed list and a breaking list, we can label it as a legitimate edit since it must be a blocked add. Finally, SINBAD extracts features from the edit subtrees and trains a simple machine learning model to classify whether subtrees are broken or not. We extract 4 categories of features that comprise the main areas where breakage manifests. Visual features include the contribution from saliency, while functional features include the contribution of interactions. Finally, we append to each subtree feature vector global features, which are aggregates of other subtrees in the same web page visit, to provide context for the classifier. As other breakage studies, our main bottleneck is datasets. But how do we get to the issues that we use for training in the first place? First, we filter out all the issues that don't have a reachable and live URL where the breakage was first reported. Next, the issues must also include the active filter list in the user's ad blocker to be able to reconstruct the exact state of the ad blocker that the user used. This is important to reproduce breakage that happens from the involvement of many different rules. Then, we try to manually reproduce each of the 2000 issues by loading the ad blocker before the fix and after the fix, and verifying what the user observed and that the breakage happens. We find that issues older than 4 months are rarely reproducible, primarily due to web page layouts and functionalities changing drastically since then. So we stop manually reproducing issues after that cutoff. So we train our subtree classifier on the main dataset comprised of 512 issues from AdGuard, which is a mainstream ad blocker, and we also include other evaluation datasets from other ad blockers. We find that the subtree classifier achieves a high 86% area under the curve score under a 5-fold cross-validation evaluation. Regarding the page level classifier, we find that if a SINBAD detects at least one broken subtree, we can reliably predict that the page is broken. By comparing to other methods, we find that SINBAD achieves a very less false positive rates compared to the heuristics used in the literature and the page graph by Smith et al. We also evaluate the generalization of SINBAD over many different datasets to verify that the performance improvement is consistent, is not dataset dependent. And to validate the importance of saliency in the interactions into SINBAD's performance, we find that the both features from saliency and interactions rank high according to the area under the curve loss ranking technique. Additionally, we manually verify that SINBAD detects many cases where it performs interactions with, for example, video players, and it can try to play the videos, but it will trigger many various dynamic breakages. Finally, we perform an error analysis over SINBAD's classifications and note some minor limitations. First, in cases where the user had some custom filter lists that are not represented correctly, SINBAD fails to reconstruct the user filter list accurately, which prevents reproducing it. In other cases, the web page is even updated in the short time between the reproducibility checks we performed and the subsequent crawl by SINBAD. We also note some edge cases. So SINBAD looks for keywords to close cookie banners before performing the saliency analysis. However, if the cookie banner language is not supported, SINBAD cannot close it, and it is counted incorrectly as a salient element because often it fills the full screen. Finally, a pertinent issue that touches on all breakage studies is that web pages serve randomized content in some cases, which would appear under any differential analysis as a change and can be considered by SINBAD as a broken subtree. So the takeaways from our approach and what we learn are: first, breakage can be seen as a disruption in the salient regions from the page. We also reiterate the data curation limitations for breakage, including the availability of the issues and the reproducibility of each breakage. We also presented SINBAD, which is the first dynamic breakage detector with a high detection rate for dynamic breakage. SINBAD also outperforms prior work, as we show, and we reiterate the errors in the previous work in terms of curating the datasets and labeling them that we try to avoid. SINBAD is also a modular pipeline, which means that if some specific components like the saliency detector or the segmentation or the interactions are improved, they can be directly integrated back into the pipeline. And thank you. And if you have any further questions, please feel free to email me or email any of my co-authors.